Okay, here we go. Take a look at this chart. Would you agree that the probabilities of having a boy or having a girl are about 50-50? They are. They're pretty close. Now, it does depend on the family. Some families have had like 9 girls in a row. And it is possible that that's just freak chance, but there's also, it seems like it runs in families, a little bit of genetics there. Like some families have lots of girls on their side of the family or whatever, or lots of boys. And in fact, worldwide, did you know that there's slightly more boys or girls born than the other? Do you know it's not really 50-50? It's really, really close, but there's a tiny edge to boys. A tiny edge to boys. And here's why. And here's a logical reason why. Boys wear out. By the end of their lifespan, usually, if you wait long enough, most of the guys in the room will be gone, and most of the girls in the room will still be here. Sad but true, guys. Hate to break it to you, but average lifespan for a woman is like 7 years longer than it is for a guy. It's a lot longer. So, I don't know. That's one way you could think of it, is that that you're averaging it out a little bit by having slightly more boys. They wear out. They break. And it probably has to do with how we're designed, you know, with guys having more muscle mass than girls. And, oh, there's a lot more difference between boys than girls than just that. But anyways, there's a lot of factors that go into it. I can't explain why guys don't last as long as girls, but anyway, there is, I just want to bring up, it's not really 50-50. Now, in some situations, you could actually have it be quite different than 50-50. Like, if you were at the doctor and your doctor told you, okay, you're about to have a baby, yay, and if you ask the doctor, that's the wrong one, if you ask the doctor, do you know what it is? The doctor might say something like, well, I know on this one there's a 50-50 chance. I can't tell. So it's either a girl or a boy. That's the first child. Look at how the chart has changed now for the second child that this family has. All of a sudden it says 70-30. That might mean that the doctor told you, I think there's about like a 70% chance that this baby is a girl. They use the ultrasound and they can like tell. Some people can actually tell by looking at somebody who's carrying the baby. Have you heard that? That basically if the baby carries a certain way, it looks like it's probably going to be a girl. Or if it carries a different way, as in if the baby's like up high, or if it's down low. Okay. Or I've heard some people say if you get a really big butt, that means it's going to be a girl. So if the woman carrying the baby notices, my gosh, my butt is so huge, and it ends up being a girl. I don't know. There's all kinds of wives' tales about how you can tell whether or not the baby's going to be a boy or a girl. So nowadays we have this amazing thing called an ultrasound, so you could actually see a little picture of the little boy or the little girl. But it's actually true that sometimes the little part that they look for to tell if it's a boy or a girl is so small that they can't tell if it's a boy or a girl. That's why we're going with the 70-30, because they might think, well, it might be a boy, but I think it's going to be a girl. All right, so anyway, and this one at the end, it was like, no, that's definitely, probably, very likely going to be a boy, 90% chance. All right, so now, given all of those, then you can have your probabilities be completely different. How do I get this number right here? Well, it comes from this times this times this. You just multiply them all together to get that. All right, now, if you think about it, these are all the things that can happen. Girl, 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 boy, girl, boy, girl, all the way down to boy, boy, boy. And when you add them all up, what do you think you get? 1, 100%, or 1. Doesn't that make sense? Those are all the things that could happen. All right, I want to make a chart with you right now that's going to be a little simpler, maybe a little bit more fun. Take out a blank sheet of paper. Would you agree that there's a chance on the way home today that you will be greeted by a dog? By a dog. Some of you guys, it's a high probability. Some of you guys, it's not. But there's a chance that you'll be greeted by a dog. I'm going to say as a group, I'm going to say there's like a 60% chance you're going to be greeted by a dog. Dog. All right. Would you agree? There is a very small chance that you'll be bitten by an iguana? Are you saying it's impossible that you're going to be bitten by an iguana? Because if so, I'm just going to have to go down to the science, life science area and grab an iguana and then bring it over here, and I can make sure it happens. Okay, so there is a chance. It's just not very big. I'm going to go with 0.01 just because even though it might be much smaller than that, it's a pain in the butt to deal with decimals that are smaller than that. So 0.01 chance of iguana bite. What do you think this third option is? If we're going to list all the things that could possibly happen to you on the way home, isn't this going to be a gigantic chart? If so, then what's the third other logical thing? Everything else. Or just not the other two. So I'm going to say neither. Neither of those things happen, but something else happens. Something will happen. So what's that going to be for a percent? 0.39, because it has to add up to how much? 100%, because all the outcomes, all the things that could happen have to add up to 100%. All right, so now you get home, and now would you agree there is a chance that you are going to really like what mom has made for dinner, or dad, or whoever makes your dinner at home? Maybe it's you, I don't know. Is there a decent chance? I don't know, you tell me. For tonight, you're going to get home and there's going to be food. Is it a good chance you're going to like it or not a good chance? I've had radically different answers from kids. Some kids it's like a only 10% chance it's something they really like, and other kids it's like 70% chance it's something they really like. So I want you to write down a number. We're going to do a really quick average. Just write down a percent. What do you think your chances are that you're going to really like what's for dinner tonight? Just write it down. And now we're going to have people say their number. It's going to be like 0.4 or 0.7 or whatever, and I want to hear all of them, and then we will do an average in our head. Okay, so as each number comes out, you need to be adjusting this average in your head a little bit. It doesn't have to be super scientific. It's kind of like counting cards. You're right. Okay, so what do you got? 0.8, 0.7, 0.9, 0.8, 0.6, 0.5, 0.2. Why is it 0.2? I'm not going to say who that was. All right. Yes? What'd you get? What was yours again? We had a 0.7 in there. 0.8, 0.7, 0.4, 0.4, 0.6, 0.6, 0.95. Ooh, like that what they serve it. Oh, your dad's a good cook? Cool. Yes. 0.9, 0.9, 0.2, 0.9, 0.9, 0.6, 0.4, 0.7, 1. Ooh, always likes what he has for dinner. Your mom would be very proud. Oh, you make your own food. So therefore, you know you're going to like it because you only make things that you like. All right, good. Yes. 0.8, 0.4, 0.1, 0.1. Back. Do they make? Is it too healthy or what is it? You're really picky eater. Okay. Yes. 0.7. Okay. That's a wide range. We had 0.1s out there and 0.95s and even a 100%. So if you had to average all of those, what do you think you'd come up to about? I'm going with 0.7. All right, so this is like dinner. This is not. And this is 0.7 and this is 0.3. I'd say on average is around 0.7, something like that. Yes, it's not coming out of the dog exactly in real life, but what this means is that if you came home and were greeted by a dog on the way home, then either you're going to like dinner or not. And if you come home with an iguana bite, either you're going to like dinner or you're not. And this is like dinner and this is not. And this is still 0.7 and 0.3. And neither. You're either going to like dinner or not. And that's 0.7 and 0.3. All right, now, what's another thing that could happen? After dinner, all right, you're going to go do homework. Now, I'd say most of you are probably going to do homework, but some of you are going to play Call of Duty instead. Or pet the cat or whatever. So this is going to be do homework or not do homework. I will pick this number because I'm scared to even ask you. Homework or not? And I'm going to say that 80% of you probably have some kind of homework on a typical night. 20% are going to blow it off and not do anything. All right. So then we got same thing here. Homework, not. See how these can be a little bit of a pain? They get to be fairly big. And when it's all said and done, we need to sum it all up. So I need to move this whole thing over so that I have room. Oh, nuts. Try that again. I need to move this whole thing over so that I have room to sum it all up at the end. So here's how you'd sum it all up at the end. This was dog with like dinner, and I did homework. And what is the probability for this person that that would happen? You take 0.6 times 0.7 times 0.8. Would you please multiply those out for me? 0.6, 0.7, and 0.8. What do you get? A little louder. What? 336. All you do is a different color here for that. 0.336. All right. I'm trying to get to the point here where you understand that the answers at the end are not always the same. Sometimes they are. Like if you're flipping a coin, it's a 50-50 chance, and then a 50-50 chance, and then a 50-50 chance, and the tables are really boring because all the answers at the end are always the same. You know, 1/8, 1/8, 1/8, 1/8, or whatever. 0.125, 0.125, 0.125. The last numbers, like a chart like this, they're all the same. Girl, girl is same probability as boy, boy, boy. You know, and all these numbers are the same, 0.125 at the end. But a lot of times in real life, that's not what happens. All right, so let's go back to the chart we were making there. And this one was, I get greeted by a dog. That's a path, it's called. And then I did not like dinner. And then I did not do homework. Let's do that one. What's 0.6 times 0.3 times 0.2? Dog, and then not like dinner, and then not do your homework, and it's what? 0.36. What happens when I add up all of the numbers that are over here, though? They add up to 1. All right. So you could figure out a probability tree for your life. Yes, there's a whole lot of little tiny probabilities then that would be all added up. But you could go crazy with something like this and figure out what's the probability that I will meet the girl of my dreams and live in this house of my dreams, which might be smaller, it might be bigger, whatever it is for you, and that I will catch a gigantic world record walleye, and that I will end up on the Olympic rowing team. Okay, so there you go. You can fish and row. Yeah, if you always just throw out a Rapala while you're rowing for practice, you'll eventually catch the big fish. Yes? All right, so you don't really have to worry about the, which one was that again? The iguana bite, and then what? Not liking dinner, and then a not like doing your homework. Was 0.00 what? 0.06. And why is it so small? Mostly because the iguana bite throws it off, right? Oh, are you saying that some of these are going to affect the others? Like if you really like dinner, you're more likely to do homework or not? Yeah. Because that is an important concept. Just okay, okay. I was talking about doing homework sometime during the night. Most kids in here do homework because they wouldn't be able to keep up decent grades without doing some homework. But if you're talking right after dinner, I hear you. That's not what I was meaning. I was meaning sometime that night they do homework. It's true. If you got bit by the iguana, maybe it's going to put you in a foul mood so you don't like dinner. And then you're just like don't want to do any homework because you're busy nursing your iguana bite. So this actually could be dependent, it's called. That's called dependent probabilities, and that means the one thing depends on the other. All right, I did want to talk about that anyway, so let's talk about it now. Dependent a lot of times happen with cards. All right, so if I have a dependent situation, I have a deck of cards here. They're giant cards, so those of you that can't see at home, and I have 8 of them. And can you see that 4 of them are 5s? All right. 1, 2, you think I'm trying to fool you with a card trick, don't you? 3, 4 of them are 5s. There are 4 5s. All right, so now, would you agree if there's 8 cards and 4 5s that there's a 50% chance that you're going to get a 5? All right, there is. So then if we go here, he got a 5. Turn it around, you can see it. He got a 5. All right, so there's a 50% chance. Now keep it. Now what if I have you try? Do you have a 50% chance? Ah, there were 8. Now there's 7. And how many 5s are in here now? 3. So you see how it affected it? So what's your chances then? 3 out of 7, which is 0.42, 42%. So his probability dropped, which makes sense, right? Less 5s in here. And he got a jack. So now there's how many 5s in here? How many cards? So now we're back to a 50% chance. See how the one thing depends on the other? Thank you. So then our chart, when we make the chart, would go like this. You're either going to get a 5 or you're not going to get a 5. What's the chances you were going to get a 5 at the beginning? 4 5s out of 8, which is also 0.5. And not, that was also 4 out of 8. How about after I got a 5, now this has to change. See, it has to change there because this path assumes I got a 5, right? So this is either 5 or not. And what does the 5 path say? 3 out of 7. And the not path? 4 out of 7. Can notice it's out of 7 instead of out of 8. All right. So in a real deck of cards, what are the things that could happen when you draw a card? Now, what if I narrow it down to 4 things could happen? What do you think I'm talking about? 4 suits. And they are hearts, spades, clubs, diamonds. All right, so there's 4 things that could happen. Do you agree they're equally likely? And what probability is it? What out of what? 13 out of 52. Very good. And they're all the same. Then, if I go down the heart path, that means I got a heart. Do you get how now I can't have heart at the same probability as it was before? Spades, clubs, diamonds. Heart is now 12 out of 51. Very good. But spades, there's 13 of them out of 51 because there is less cards in the deck. All right, so those are dependent events. If you take a card out and then you put it back into the deck, then it makes it not depend again on what you got the first time, right? So you can make card tricks independent, but a lot of times card problems, if you take the card out and you keep it out, then it depends on what card you got the first time. Yes? Oh, it's a couple hours of understanding the concept, but then practicing counting cards would be the hard part. I've never really taken it seriously. I did it with a friend a couple times and counting cards, and it's really, really hard to do. There were times when I thought that I had an advantage, but the casinos know this, and if somebody like you and I can figure it out this easily, they don't want to make it easy for people to have an advantage at the casino. So that's why they have so many decks. They have so many decks in the shoe, it's called. So you'll have like 5 decks of cards, literally. So you got to be counting so many cards by the end that it's really hard to keep track of it all. But you can have an advantage by the end. And a lot of times you don't have an advantage. You can play, a lot, play lots of hands, and all of a sudden it comes out kind of equal. There's no, you didn't get more 10s than normal. You didn't get less. You kind of get an average amount. So it's only certain times when it ends up that it actually works out for you. So you can't just say, "Ooh, I'm going to learn how to count cards and make lots of money." There's still some luck involved, whether or not you had the lots of big cards come out or not. All right, so I want you to figure out a dependent probability here. I want you to figure out, don't have to make a big tree. You have to know how they are made to be able to do this, but I want you to figure out the probability that a kid draws a 5 out and then draws another 5 out. They did not place it in between. Figure out the probability on paper. Don't have to make a tree or anything. This little deck right here, this has got 8 cards in it, and then 4 of them are 5s. I want the probability that you're going to get 2 5s when I give you a chance to draw. Actually, if you draw them at the same time, it's just like if you draw them one at a time. Because if you get one, all of a sudden your probabilities have changed of getting another one, right? So if you're grabbing 2 out or whether you're grabbing one at a time, same. So think of it as one at a time, it's easier. All right, so what's the chances of that first 5? That's really easy. 4/8, 0.5. And you times by 3/7, and what did you get? So there's only a 21% chance that happens. Could I have a kid try it and get it right away? No, I was talking about the small deck. You must have missed that little thing. If you were doing the whole deck, that would be a totally different problem. All right, so let's try it. Pick a card, any card. She got a jack right off the bat. Okay, so she didn't get 2 5s, right? So how many people should I have to try on average before I get somebody to win? If I do 5 people and one of them win, that's about 20%. That would be right. So if I try 5 people, then one of them should win. All right, see if we can get, shuffle them around a little bit. All right, there we go. See if we can get 2 5s. You got a 9. Okay. Oh, I got to move that around. Okay. Hit it. Oh, he pulls out a 5. He's got a chance. Now what are his chances? Think about it. 3 7s. 3 and 7 chance now. He's feeling it. Oh, so close. But so far away. All right. All right, so we've had 3 people fail. 1 got close. Not in life, just... No! That 9's been really lucky. All right. Lid key. He's got 1. Oh, I'm going to reshuffle this deck to see if he can come and pull off the other one. He's got a 5, and he's got another 5. Hold him up, prove it to him. He's got the double 5. Very nice. Look at that. There were 5 people, and one of them got it. Is that always going to happen? No. But on average, that's about what should have happened. All right. So, I'm happy that you're understanding that if I take 1 card out, it changes the probability. That's called dependent. So your homework is just like that. And I want to spend some of our time now just working on your homework. Your homework is, it's kind of weird today because I've talked over 2 concepts that are today's lesson and tomorrow's lesson so that we'd free up time so that tomorrow all you have to do is take the CML test. So today's and tomorrow's homework are all put into today, meaning there's 2 worksheets, but you don't have to do them both today. In fact, you don't have to do them both until Monday. All right, so you have 2 worksheets, not due till Monday. And I'm going to have you throw out a couple problems because there's just, even as it is, that's a lot to do. So I'm going to cut out a few. So start with this one, and you can do number 1 and number 2 and number 3 without worrying that those are ones I'm going to throw out. I'm going to throw out some on the backside, but start on this right now. Do problems 1, 2, and 3. I think you'll find them very easy. I'm going to keep the video on just for a second because I want to help you with 1 problem off the worksheets, and that'll help the people at home with 1 problem. All right, looking at the worksheet called 12.2 Counting Outcomes. Problem 1, 2, and 3 are easy. So, flip it to the back side. Number 8, drawing the tree diagrams can get big, and I think 8C goes over the top. We don't need you to make a doing 4 separate drawings or flippings of coins. It ends up being like a ton. It's a giant tree, and there's no room for it. So cross off 8C. All right, the only one I'm having you skip on that one is 8C. Just because that does save you a lot of time, believe it or not. All right. And that worksheet's real easy, so I don't think I need to help you much more with that. Then the other worksheet is 12.2, worksheet A, and that's coming out right now. And there are definitely some to skip here. 1, 2, 3, 4, 5. 2, 3, 4, 5. 1, 2, 3. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Okay. On this worksheet, 12.2a, it's just coming back now. You may skip problem 2 in its entirety. There's an A, B, C, and a D, so you can skip number 2. You're not listening and you're missing out on some good stuff on the worksheet I just gave you. Number 2, you may skip A, B, C, and D. That's a lot of problems to skip. All right, now number 12.2, worksheet A, the very first problem. I want to start it with you together. All right, you choose 2 cards, one at a time, from a deck of 52 playing cards. Remember that a normal deck has 4 suits, so there's 13 clubs, 13 spades, 13 hearts, and 13 diamonds. You do not replace the first card, meaning you took the card out and you keep it out. A, are these independent or dependent? Dependent, that's easy. Part B, draw a tree. Well, the first thing people do that is a mistake sometimes is they think that there's like a million possibilities. There's 52 possibilities. Not when you boil it down to just talking about clubs, spades, hearts, and diamonds. Then there's 4 possibilities. So start your tree like this. Clubs, spades, hearts, diamonds. And after you've drawn or before we should do that, we should say what's on each branch, the probabilities on each branch. And these are easy, because there's 13 out of 52, and if you divide that, what percent do you think that would be? 1/4, which is the same as 0.25. But the other ones are not so easy, because after I've drawn a club, now there are still 4 things I could get. I could get a club, a spade, a heart, or a diamond. But they're much more complicated to figure out. What's the probability of getting a club now? Think of it as a fraction, not a decimal. There's 12 clubs left instead of 13 out of 51. Because there was 52 cards in the first place, but you already got a club out. So now there's only 51 cards. So now to get this final answer down here, you're going to need to multiply 0.25 times 12 51sts. And that'll be a decimal, and you'll put it in the box. And yeah, you're going to have to squeeze in all of these. Yes, this is a pain, but that's why I cut out one of the problems for you. And remember, you have Thursday night, Friday night, Saturday night, and Sunday night, 4 nights to get this done. So take your time, do it right. The first worksheet I gave you is pretty easy. The second one's definitely a little harder. All right, now, one of the questions they're going to ask you is, what's the probability of getting at least 1 heart? Clubs, spades, hearts, diamonds. Clubs, spades, hearts, diamonds. Clubs, spades, hearts, diamonds. Would you agree that all 4 of these are going to have at least 1 club? Because they got a club on the first draw, right? And this one's got at least 1 club. And this one's got at least 1 club. And this one's got at least 1 club. So find the probability. I started by saying hearts, but then I just did clubs. But the same idea. All of these here added together are the probability I'll have at least 1 club. You got to think it through like that and figure out which ones have at least 1 club. And then find all of those answers and then add them all up. Okay, because all of the spots I just put an arrow to are paths that had at least 1 was a club. All right, so that's the hardest kind of problem that there is. All right, get to work. Need help? Come on up and ask.